Hi. In this video, we're going to be, going to be going over this stability practice CG VCG, which is something we gave you in class to work on here. It's got 6 problems on it. So we're going to do problems 1, 3, and 5. Okay? So the first problem, it turns out you can do most of these problems, certainly this first one and the second one, you can either do it by theory of moments or you can do it by GG. Let's go ahead and we'll do it by theory of moments first. Theory of moments is a way of calculating kg. Okay, so kg is going to equal total moments divided by total weights. Okay, and to calculate these total moments and total weights, we're going to set up a table. And the table is going to look something like this: weight times distance equals moments. Okay, so we look at this first problem, and you have to read along on your own sheet there, but it says your vessel displaces 475 tons. Okay. The existing deck cargo has a center of gravity of 2.6 feet above the deck and weighs 22 tons. If you load 16 tons of cargo with an estimated center of gravity 8 inches above the deck, what is the final center of gravity of the deck cargo? Okay, well, it turns out that in this problem, they're actually not asking you to calculate the center of gravity of the whole ship. They're asking you to calculate the center of gravity of just the deck cargo. All right, and that's a little bit tricky, okay? So in this problem, actually, we are not going to consider the entire weight of the vessel. They want to know what is the final center of gravity of the deck cargo, and the part that's missing in there is from the height of the deck, okay? So in this problem, for theory of moments, our weight, well, the original weight of deck cargo is 22 tons. And the center of gravity of that weight is 2.6 feet. Now, that's not 2.6 feet above the keel. It's 2.6 feet above the deck, because that's actually what they're asking in this problem. So if I multiply those two together, I get 57.2 foot tons. Okay, that's the moment. Now, what's my second weight? Well, my second weight is I'm going to load 16 tons of cargo. Okay, so what I'm going to do now is I'm going to load, so that's going to be plus, it's going to be 16 tons. Now, they tell me that it's 8 inches above the deck. Well, the original cargo was 2.6 feet above the deck. Now I'm going to be 8 inches above the deck. Well, it turns out that this is in feet, this is in inches. I can't have that. I've got different units. I'm going to have to put it all into feet or all into inches. Well, since I've already got this one in feet, I think I'm just going to keep it in feet. So I've got 8 inches. And if I want to convert that to feet, I'm going to multiply that by 1 foot for every 12 inches. The inches go away. So it's going to be 8 over 12, which if you do that should turn out to be 0.667. Okay? Which, okay, that's 0.667 feet. So that moment is going to turn out to be 10.6 foot tons. All right? So, great. Now, it turns out that my kg is the total moments divided by the total weight. So I got to sum all my weights and sum all my moments. So let's do that. So 16 and 22 turns out to be 38 tons. And 57.2 and 10.6 turns out to be something like 67.8 foot tons. And now I've got to take this number, 67.8, which is my total moments, and divide it by 38 tons, which is my total weights. Tons go away, and I'm left with feet. So it turns out that my kg is now 1.78 feet above the deck. And if you think about it, what was the original kg of the deck cargo? Well, the original cargo was the 22 tons at 2.6 feet. Well, I'm taking 16 tons and I'm adding it lower than that. So that should make my kg go down, which it does. Okay? So that's problem number 1, done by theory of moments. All right? Now I could do the same problem. I'm going to do it using the GG formula. So I'll do that in a different color marker. So GG, this is the same problem. GG prime equals weight times distance divided by displacement. Okay? Now we got to figure out what all these things are. Well, we're going to use this formula. It's easiest to use this formula when there's only one weight moving. Well, it turns out that really in this problem, there's only one weight that's moving. We came into port, let's say, with 22 tons at 2.6. And now we're loading 16 tons at 0.667. So, what's my weight going to be? Well, if you look on page 58 of your book, you'll see all the rules for GG. Your weight is going to be the weight of the object, the small weight of the object that you're moving. In this case, it's going to be 16 tons. So that's going to be 16 tons times the distance. Now, the distance is not going to be from the keel. It's going to be the distance between the original G and where I'm sticking the new stuff. So originally, my kg was at, or my center of gravity of the deck cargo was at 2.6 feet. Okay? And I'm going to put something at 0.667. So this distance is actually the distance between the original center of gravity of the deck cargo and the center of gravity of what I'm changing, which is 0.667. Okay? Now, what's the displacement going to be? Well, it's going to be the entire displacement of the stuff that I'm talking about here. In this case, you might be tempted to put in that 475, but again, they're not asking for the total center of gravity of the vessel. They just want the deck cargo. So what we're going to do here is we're going to put in how much was the original cargo? 22 tons. What is the cargo I've just added? 16. Okay? And now, when I do all this math, I should get a GG prime that is 0.81 feet. Now, what am I going to do with that? Well, first of all, it's a smaller number than that. This is the total distance from the keel to the center of gravity of the overall. Well, actually, this is the total distance from the deck to the center of gravity of all the deck cargo. But this is actually how far the center of gravity is moved after we put that weight, we added that deck cargo. Okay? So, if I had a deck cargo with a gravity of 2.7 and I put something at 0.667, which way is the center of gravity going to move? Well, this is below that. If I'm adding, my center of gravity is going to move down. Okay? Well, it's going to move down 0.81 feet. Well, what was the original center of gravity? Well, the original center of gravity, okay, of the 22 tons was 2.6 feet. So, if it moves down, I'm going to subtract 0.81 from that, and I will get a kg prime of 1.79, which is basically the same, okay, as doing it by the theory of moments. So we did this, looking at all the weights, and we did this, really looking at moving the one weight. So that was problem 1, okay? Now you can do problem number 2. I'm going to give you the answer for problem number 2, and then give you something to shoot for. All right? So the answer for problem 1 is 1.79, 1.78. That's the overall center of gravity of that deck cargo. All right. Problem 2, the answer should turn out to be 2.08. Okay? And whether you do it by GG or theory of moments, 2.08 is what you're shooting for. Okay? All right. Let's do problem 3 now. Okay. So, problem 3 on this same sheet. And, okay. Well, in this problem, they tell you that your vessel displaces 422 tons. Okay? So my displacement is 422 tons, total displacement. And I have about 6 tons of fish. Okay? So my small weight is going to be 6 tons. And they want to know, what is the shift of gravity if I shift that fish down 7 feet? Okay, I'm going to take this 6 tons of fish, maybe it's on deck, and I'm going to shift it down 7 feet. And they want to know, well, what is going to be the change in the center of gravity? Well, if you wanted to do this by theory of moments, you're going to have a problem. Because the problem is that, well, we don't have a kg of the ship. This is a shift problem. They're telling you it's shifting. So we actually have to use GG for this. Okay? So let's write the GG prime formula again. It's weight times distance divided by displacement. Well, what is the weight going to be? It's going to be the weight of the individual thing that we're moving. So, in this case, it's going to be 6 tons. All right? I don't know what I'm doing there. Now, what's the distance going to be? Well, I don't have any kgs to subtract this time. They tell me what the shift is. This formula is really called shift of g. They're telling me how much the shift is. So I'm already done. I'm just going to use 7 feet. Now, what's my displacement? It turns out my displacement is going to be the displacement after the fact. Well, what did I do? Well, I had 422 tons, and I moved 6 tons down. I didn't load 6 tons. I didn't discharge 6 tons. I just shifted it. So it turns out that my displacement doesn't change. It's still 422. Okay? Which, when you do the math, turns out to 0.0995, which really turns out to 0.1. Okay? So that's the shift. It's 0.1 feet. That's how much it moved. Okay? 0.1 foot, 1/10 of a foot. So, a little bit more than an inch. Well, which way did it shift? Did it go up or down? Well, they tell me it went down. So this is going to be a shift of 0.1 feet down. Okay? We don't know what the original kg was, but we do know that it's gone down 0.1 feet, which means the boat is slightly more stable. Okay? GM is just a little bit bigger. Okay, so that was number 3. And we cannot do this by theory of moments because we don't have an original kg for for either the ship. So we can't actually do theory of moments. This is one of the few situations where we could not. A pure shift. So you should now do question number 4, and the answer for question number 4 is going to be 0.3 feet down. Okay? So give that one a shot. All right. Now we're going to do question 5. Question 5 is a long problem, and it's a little bit tedious. I'm going to walk you through it step by step. So, question 5, all right, you have to look on your sheet because I can't really show this to you very well with this video. I don't suppose I could walk up to the camera and, you know, here's the problem, all right? But anyway, you can just read that yourself. But there are 4 different parcels. So let's read the question. You are on a supply run for an OSG, an offshore for an offshore drilling rig. And on board you have the cargo listed. So there's 4 different types of cargo that we've got on there. What is the height above the main deck of the center of gravity of this cargo? Okay, again, in this problem, they're not asking us for the overall center of gravity for the ship. They just want to know what is the center of gravity of the deck cargo above the deck. Okay? So we could do theory of moments calculating it above the deck, and I think that's actually going to be the way we want to do it. We could also do GG here, but it's a serious pain in the butt. Okay? It would be much better doing theory of moments here. So we're going to have, for this, theory of moments says you have weight times distance equals moments. So we're going to have to do some calculating. But the thing here is that as we look at these different parcels, drill casing, 6 pallets of oak planking, crated piping and machine parts, drill pipe, it turns out that we got all kinds of units in there. And if you look at this first one, you know, you've got long, anyway, we're going to go through one step by step, but we have to figure out what units we're going to do. We're either going to use feet or inches, and then for distance, and then we're either going to use tons or pounds for weights. So let's figure out what's going to be the easiest thing. Let's first do distance. We got 16-inch diameter, foot long, feet crated, 8. I'm going to go ahead and I'm going to keep everything in feet. And then let's look at the weights. Problem 1, the drill casings, you're starting off with 1.72 tons. Part 2, consignment 2, the pallets of oak planking, that's also in tons. Consignment 3, that's in pounds. We're going to have to convert that to tons. And 4 is in tons already. So the easiest thing to do is going to be to convert the 660 pounds to tons. So let's do this whole thing. Well, it turns out we're going to need one more column, quantity, okay? So, the drill casings, they are 16 inches in diameter by 30 feet long. There are 20 lengths, so the quantity, this is going to be the first one. There's 20 of these things, okay? And each one of those weighs 1.72 tons, okay? Now, what is the distance above the deck for the center of gravity of that? Well, they're 16-inch diameter and 30 feet long. Well, we don't actually care about the 30 feet long. We're only interested in how high they are above the deck, which is 16 inches. So the distance is really going to be half of 16. 16 is the entire pipe, okay? But 8 inches is the height of the center of that gravity. So it's going to be 8 inches, okay? Really, you could say it's 16 divided by 2. But I want to have this in feet. So I'm going to multiply this by 1 foot for every 12 inches. And now that's going to give me feet, and that's going to convert back to 0.667, okay? So now I can take 20 times 1.72 times 0.667, and that's going to give me my overall moments, which should end up being, this weight should be 34.4, all right? 34.4 times 0.67 is going to equal 22.94 feet, okay? Cool. Now let's do the second deck cargo. Okay, we have 6 pallets of oak planking. So my quantity is 6. It's stowed 2 pallets high. So if we think about this, here's one pallet, there's another pallet, so they're stacked on top of each other. Okay? They're stowed 2 pallets high. Each pallet weighs 2.2 tons. So 2.2, I'm going to have to multiply that by 6 to get my weight. And each pallet is 3 feet high. So this is 3 feet, this is 6 feet, so the center of gravity is 3 feet. So my distance is 3 feet. Done. So what's 6 times 2.2? That should be 12, what should that? 13.2. So 13.2 times 3 is going to give me 39.60. Okay? Cool. This is foot tons, and this is foot tons. Okay, what's our third item? Our third item is crated piping and machine parts. There's 8 crates. That's my quantity. And my weight is 660 pounds. Okay, now here, 660 pounds. Okay? Well, now I need to convert that from pounds to tons. It turns out that a long ton is 2,240 pounds. So this is going to be 1 ton for every 2,240 pounds. Pounds goes away, and now I'm going to be left with tons. So what's my weight there? If I multiply 8 times 660 divided by 2,240, I get 2.36 tons. Okay? Cool. Each crate is stowed singly. They're 8 feet long, 4 feet wide, 3 feet high. So if the crate is 3 feet high, the center of gravity is going to be half of 3 feet. It's going to be 1.5 feet. So 2.36 times 1.5, in the previous example it was those two, that's going to equal 3.54. Okay, last parcel. I have drill pipe, 6 inches in diameter, 30 feet long. Okay, so it's 6 inches diameter. The center of gravity should be 3 inches diameter. Okay, 3 inches. I have 120 lengths. Woo, there's quite a few of those. Times 0.644. 0.644. That's going to equal 77.28 tons. Okay, what's my distance going to be? Well, they tell me that the pipe is 1.1 feet above. So, now if I multiply that times that, I will get 85.78 foot tons. Okay, now, theory of moments says divide the total moments by the total weights. So my total moments, now I got to add all this stuff. That's going to be 151.86. And then my total weights are these 4, right? The quantity times the weight, blah, blah, blah. So I got to add these 4 now. Turns out that that is 127.24 tons. Okay, so I'm going to take this now. I'm going to bring this over here. I'm going to divide 151.86 by 127.24. And when I do that, I'm going to get my kg. And that's going to be 1.19 feet. Okay? And that's how you do that problem. That was problem 5. And problem 6, I'm going to let you do on your own. You're going to have to do the same thing. Get it all into foot tons or pounds or whatever it is you want to do, whichever you think is easiest. And at the end of the day, for number 6, the kg is going to equal 1.05 feet. That's the answer you're trying to get. Good luck.